Hello and welcome to Challenge Accepted, the podcast that explores comprehensive engineering solutions for complex projects. In each season, we dive into a different project sector with a panel of experts discussing how they've tackled their industry's most complex challenges. This season, we're diving into PFAS, exploring the evolving regulations and how we're helping clients navigate this complex and rapidly changing landscape. Hi, everyone. My name is Adam Hackenberg, and I am your host for this season of Challenge Accepted. I am a senior project manager in Langen's Philadelphia office and one of the firm's PFAS practice leaders. Today's episode is all about innovation, the trials and triumphs in PFAS technology solutions. We'll explore why PFAS technology solutions remain somewhat elusive, what's working, and where the next breakthroughs might come from. Joining me today are Amita Uka, Anna Willett, two of Langen's PFAS treatment and remediation subject matter experts. Amita has a PhD in environmental science and is a senior scientist in our Princeton, New Jersey office. And Anna is a senior chemical engineer in Arlington, Virginia. I'm also really pleased today to be joined by a special guest, Shailene Thomas. Shailene is a senior emerging contaminants program manager at Battelle, which is a global technology, consulting, and analytical laboratory innovating in biology, chemistry, and advanced materials. Thank you so much for joining us today, Shailene. Before we get into the conversation here, I just want to acknowledge that there are a lot of areas of PFAS innovation that are ongoing right now. Everything from analytical methods to an evolving understanding of the physiochemical properties and environmental behavior of these contaminants to the use of digital solutions and machine learning to manage and evaluate vast data sets. But today, we're really going to try to focus in on treatment and remediation technology innovation. So with that, Shailene, I sort of want to start out with you here because you are very much in the space of R&D work and specifically PFAS R&D work. I want our listeners to understand a little bit about the R&D process, specifically the PFAS R&D process. Where are the ideas coming from? Who's doing the research? How does a concept move from theory to commercialization? So maybe you can get us kicked off by talking about those things.
Certainly. Thank you so much for the opportunity, Adam, and for Langen. This has been really great experience so far. So the research and development framework that Battelle follows, as do many other federal government entities and global entities, follows this technical readiness level process. It's a 9-step process. It was first developed by NASA back in the 1970s as a way to really help orchestrate and funnel any type of technology development through a process that was common to all. The technical readiness levels, TRLs as they're called, TRL 1 to 3 is that early concept stage where you are testing research and concepts. The TRL 4 to 6, that is when you're getting out into the field. You're doing demonstration and validation. And then the TRL 7 to 9, of course, is when you're driven into commercialization. The timeline generally that supports this technology process for any given technology out there is over 10 years. I think we have to give ourselves some grace as PFAS experts and PFAS practitioners. We try our best, and we are doing great in that as it relates to PFAS to move it faster. There's really no universal rate of failure for technology commercialization through this process either. It does vary substantially, but it is acknowledged by many sources that an estimated 95% of innovations never, ever reach the market. And most of that failing happens in that middle TRL 4 to 6 stage where you're doing demonstration and validation. There's many factors and reasons for that, from market misalignment and financial resource constraint to operational challenges, regulatory factors, and technology implementation issues, which I think we'll probably get into a little bit more today.
Yeah, so Shailene, I want to ask you this technology readiness level process that you described as the thing that's been adopted by Battelle. Is that a widely recognized process? Or others following that too?
It is widely recognized by many government entities. The federal government specifically, like the U.S. Department of Defense, follows that process. Department of Energy, the European Commission. I was at an event in Australia just 2 months ago, and talked about concept to commercialization there. They do not follow that process. They are not familiar with that. So it is globally adopted, but not broadly globally adopted.
And you mentioned the success and failure rate, which, it's astonishing to hear that 95% of all concepts fail. I think that's what I heard you say, right? Now, when you said that, were you talking about globally in general with the technology development process, or is that just specific to PFAS tech development?
That is global in general. It's very, very difficult to put any type of number on it as it relates to PFAS. I don't know that anyone has done that, but that reference was global.
Okay. I want to give Anna a chance to chime in here and transition to another related question. And that is comparing the process of treatment and remediation research and development that we're seeing for PFAS to prior waves of R&D for other contaminants. And I'm wondering if you can speak to that subject and maybe tell us from your perspective, what are some of the things, if there are things, do you feel are unique and different or maybe especially challenging about PFAS technology development as compared to some of the prior contaminants that have come through this cycle?
Sure. Thanks, Adam. Primarily and foremost is the unique chemical structure of PFAS related to the strength of the fluorine carbon bond. And they're resistant, particularly the regulated PFAS, are resistant to chemical degradation, either oxidation or reduction or biodegradation. And this differs from other quote unquote traditional contaminants like chlorinated solvents, which are biodegradable, which was a key research R&D, effort in the 2000s. Same status for chemical oxidation and chemical reduction. They're just not destructive approaches that aren't high energy that can be used. And this combined with the extremely low treatment targets or cleanup targets, which are based on regulatory standards, for example, the drinking water standard for PFOS and PFOA for PPT, which is 3 orders of magnitude less than what we were used to with coordinated solvents. Those two factors make it very challenging to find technologies that will make a difference and not make the problem worse. And certainly, for practitioners who need to clean up now, there's very few technologies that are accepted by the regulatory authorities, including US EPA. And what's interesting is that some technologies that were like groundwater extraction, aka pump and treat, which had been utilized for chlorinated solvents and then deemed inefficient and costly in some cases and ineffective, are being resurrected to treat PFAS because groundwater extraction is one of the only ways to get PFAS out of the ground and treatment above ground. And so it's been interesting to see how the thought process has changed with respect to groundwater extraction. The good news is we have 20 years of experience optimizing groundwater extraction, so these systems can be designed avoiding some of the pitfalls that were experienced in the past. And you see a similar scenario with destructive approaches in that incineration, specifically hazardous waste incineration, had not been considered a technology, but is very effective for PFAS treatment. Of course, it's still under the applied research process in that measuring the products of incomplete combustion at the other end is still being sorted out, but still hazardous waste incineration most likely will become a technology that's primarily recommended for PFAS, and that was not the case with chlorinated solvents and hydrocarbons, for example.
Yeah, so it sounds like there are chemical specific challenges that could impede the progress on technology development for PFAS treatment and remediation. But I wonder, given what you just said, Anna, I think you mentioned that we've got 20 or 30 years of experience developing and perfecting pump and treat technology. Like, do we have a leg up now because we've gone through prior waves of technology development? What's given us a leg up? Are we able to leverage knowledge that we've gained through those previous processes and established institutions and funding sources to make this go faster? Shailene, you said, let's expect that it's going to be a 10-year technology development process, but what's given us a leg up based on our prior experience? And is there anything new out there right now that is giving us an advantage in trying to accelerate tech development for PFAS? I mean, I know there's a sense of urgency about this in a lot of circles.
So I think specifically for PFAS, certainly we know more about groundwater extraction than we did 30 years ago. And applying it from the start instead of optimizing after the system has been up and running for 5 years. Instead, for PFAS contamination, groundwater contamination problems, the system can be designed optimally from the start. But I was going to go back to another approach that's being used for treating PFAS in water is absorptive media. So you may have heard of GAC or exchange resin, which are quote unquote old technologies. They've been used for maybe 50 years for cleanup of water or treatment of water. And at this point, having the understanding of the PFAS chemistry, this progress that has been made in the last few years, I think is going to lead to designing PFAS specific, or already is in the process of designing PFAS specific adsorbents that improve on the behavior of GAC and ion exchange resin, for example. And I think that's going to happen quicker because we have the experience from the past, even if PFAS is totally chemically different in nature than other contaminants.
That's a really important point, Anna. I'm maybe skipping ahead in the conversation a little bit here, but I think you opened the door, so I want to run with it a little bit. It sounds like what you're saying is that maybe there's been a lot of focus on what's the new shiny technology that we hope is going to solve all of our problems. But I think what I hear you more saying, and Amit, I know you might have something to say about this too, maybe a focus should be or is improving the technologies that we've already got to be more specific, more targeted to PFAS, more efficient and more cost effective. Is that a fair characterization of maybe where we are?
Yeah, definitely. So I think what I would say is Anna pointed out some of the previous technologies that, let's say, are applicable, not applicable. And now we know some of them are applicable, but they are not up to the mark because PFAS chemistry is so complex. So there is definitely an element of adapting, maturing the technologies so that match what is required of PFAS treatment. And then it's not just the chemistry, it's also the scale at which we really need to treat. The contamination with PFAS is practically in everything that is around us. And we have not been faced with this kind of problem before, the scale of contamination. Also, the levels to which we are going to be treating are much lower than the others. So I think there is a chemistry issue that adapting existing technologies, making them better, and then, of course, looking around and maybe developing additional technologies. But applying whichever technology we go with to the scale that is needed and to the levels of cleanup that are needed. I think those are also challenges that should not be overlooked.
While we wait for the new technology to go through the technology readiness levels and whichever of that 5% that's going to become successful, we need to be able to apply the tools we have now. And so improving those for PFAS, knowing the specific chemistry is what is going to be used for solutions right now versus in 5, 10 years. So we can cross our fingers for something great to happen. But right now, we've got to use the tools we have at hand. The innovation lies, in my opinion, in improving those, specifically for PFAS. And I do want to point out foam fractionation, which is technology making use of the surfactant properties of PFAS, is not used for other contaminants. In traditional cleanups, they had some niche applications, but it's really been developed quickly as PFAS has emerged and now is an accepted technology. It's a separation and concentration technology, but I think it's an interesting case study how that process did exist for fish tanks and other applications like that, aquariums, and it was customized keeping in mind the PFAS specific chemistry. And there's several commercially available units that are specific for PFAS and have been optimized for that use.
Yeah, so that's the point that we were trying to emphasize. It's an existing technology that we're improving upon, not necessarily a brand new technology that's going to save the day. So we talked a little bit about things that have given us a leg up in the R&D technology innovation development process for PFAS, the fact that we've gone through these prior waves, there is funding available, and we've got a pretty good body of experience under our belts. But I want to shift now to talk a little bit about what's keeping us back. What are the challenges that are keeping us from making progress more rapidly? Maybe not so much focusing on technology challenges. Anna, you already talked about the nature of the contaminants and how that poses a certain challenge, but I'm thinking maybe there are also barriers that are softer, like institutional barriers and regulatory barriers and more philosophical things. So, Amita, maybe you can get us started out with this conversation. And I know, Shailene, you probably will have some things to say about this one too.
Sure. When it comes to thinking about barriers for innovation, I like to think about it with an analogy, like a marketplace analogy, right? Is there a demand? And if there is a demand, there will be supply. So specifically for PFAS, looking backwards, from where we came from, we were trying to develop our understanding of its chemistry, its effects, its health effects, risk. And now we are developing technologies and regulations for treatment management as well. I think it's important to understand for this process of innovation from this idea to commercialization, there is not only like physical challenges that the researchers face and the innovators face, but there is also inertia. I think of it like as a traffic light. The traffic light becomes green, but you can't still go. It takes time. So there is definitely that inertia that comes into play. And then there are other factors, such as you mentioned regulatory acceptance, that the technologies, if they're tried and tested, then people would be interested in applying them. But the researchers and innovators cannot test them if they don't get opportunity. So it's kind of a chicken and egg issue. Specifically, and we can talk about drinking water treatment, which is widely known that for drinking water treatment, public water systems, they require an approval of state and local agencies, as well as the National Sanitation Foundation, NSF, American Standard Institute, ANSI standards for safety and performance. Speaking of accepted technologies, there is a DoD approval program for environmental security technology certification through which different technologies can be validated. Another example of accepted technologies would be Florida Department of Environmental Protection's accepted list of technologies. And this is not just for PFAS, this is for other contaminants as well. So now we're talking what is accepted, not just to the regulators, but also to the governing bodies. These regulations are not crystal clear. They don't come from one place. They come from states. They come from the federal level. It's a really complex regulatory framework that needs to be navigated every time you're thinking of treating, whether I'm in New York, New Jersey, or I'm on the West Coast somewhere. And also, I would like to mention, we did talk about funding before, but there are definitely some funding constraints, and the funding changes with the year. It's volatile in nature. Lastly, but not the least, when it's the time to try out new technologies, there's fear of unknown that needs to be overcome. And then there are also some unrealistic expectations about what the treatment can achieve. So all these together, I think, build up that inertia, which any system naturally has.
Yeah, Shailene, do you want to chime in on this?
Certainly. I talked earlier about the technical readiness levels and how many adopt that process. And to your point of barriers and challenges, that's only one set of barriers and challenges. There is another scale upon which many are using, especially in the federal government, and it's called the adoption readiness scale. And that takes into account a lot of these other factors that impede progress for technology commercialization. I mentioned earlier the 10-year process and how the success rate is very, very small. We all know that that happens during that middle TRL or technical readiness level 4 to 6, where they call it the valley of death, so to speak. And the valley of death doesn't happen because these technologies aren't valid, they aren't technically appropriate and working. That's a small percentage of them, really. A lot of the reasons are related to the adoption readiness. Funding cycles often drop off. You see funding early on in a process in early stage research. You see investment in the commercialization process and back up to that. But in that middle stage where there's the highest uncertainty and risk, finances often fall off. The other thing I think institutionally across many programs that are out there, Amita did some great reference to them. Department of Defense Innovation Unit is an example where they had the ESTCP process, which is very slow, very prescribed. They tried to add PFAS to this Defense Innovation Unit process to expedite that TRL process. so that they could more expeditiously evaluate different technologies. So that's a primary example of ways to overcome some of those adoption obstacles. Another one, Amita referenced regulatory acceptance. The Interstate Technology Regulatory Council and their PFAS work, they have a table that they have pulled together that shows types of technology, not specific providers, but types of technology and where it is in the development process, just in an effort to really try and push that regulatory acceptance, as ITRC is a body representing all the regulators around the US. It's a voice to say we accept some of these things, or this is what's out there as we know it.
Right, because regulators are a big part of that organization, the ITRC. So if they have a say in reporting out on where technologies are in the process, that may make them more inclined to allow some innovative technologies to be tried at sites in their respective states. So, yeah, that's really great. And speaking of states, I want to go back to something that you said, about the acceptance lists. We've got these lists of accepted technologies that you referenced, and a lot of that has to do with drinking water. Is that something that is helpful to have a list of accepted technologies that are go-tos so that we can quickly reference that list and choose something? Or is that an impediment to innovation? And as a follow-up question to that, again, with respect to drinking water, are there states that are providing money or funding to try different things related to drinking water treatment? Is that something that's happening?
Yes, so let me answer the first part of your question as to how do those accepted technology lists, whether they help or hurt. I think it's a double-edged sword. Onto that list is, I'm pretty sure it's not an easy process. So there is a lot of responsibility on the innovators and researchers to demonstrate the effectiveness of the technologies and readiness of those technologies. Thinking about from a practitioner's point of view, when we work with clients, there definitely is more willingness to use technologies that are already on that list. For the state of Florida, definitely, I would say that I have worked on projects for other contaminants as well. It makes process easier. It's not that you cannot use technologies that are not on that list. And then talking about state funding, there are definitely programs, especially for drinking water pilot testing, that are state funded for economically disadvantaged communities, specifically where funding is available for pilot testing or drinking water treatment technologies, and then further with implementation.
Thank you, Amita. That's helpful. I think one of the other things that you mentioned is that there's oftentimes a reluctance on the part of the regulated community, let's say, to be experimental on their real project sites. I know we've talked a little bit about that before, and I'm wondering if we can expand on that idea just a bit. What are the potential disadvantages in the eyes of the regulated community to attempting some R&D of new tech on their project sites? And how can we encourage the regulated community and regulators alike to get a little bit more comfortable with the idea that we do need to have test sites for these technologies, and that is a recognized barrier that needs to be overcome?
I think encouraging states to learn from other states. So there's such a wide difference between the understanding and approach to PFAS among the states. And so one of the premises behind organizations like ITRC and AWWA, American Water Works Association, which focuses on drinking water, is to take knowledge from states or interpret knowledge from states that have made progress and then vet that or make it available to other states as a service. And so AWWA, for example, has published a framework for a title is Framework for Approaching Permit and Plan Approval, but it basically goes through all the different types of pilot testing for PFAS drinking water treatment technologies that has been done, includes bench and pilot testing, and then how do you make use of that information so that you don't have to repeat the process over and over again in other states where that pilot test didn't take place, for example. And so that could be really useful in allowing more uniform acceptance of approaches across the country. And you could do a similar type of exercise with other treatment of other environmental media. It's just that treatment of PFAS in drinking water, for a number of reasons, has advanced faster than other environmental media like groundwater, certainly wastewater, although we are seeing some testing for wastewater treatment at the states as well.
Yeah, I mean, rightfully so, right? Treatment of drinking water as a top priority makes a lot of sense, and now we're maybe moving into some other areas, and I want to pick back up with that in a bit, but I want to hear first if Shailene has anything to add to this conversation about how do we encourage more liberal R&D on real project sites. I think beyond DoD, right? Or Shailene, earlier you mentioned that a lot of this work that's being done right now in the R&D space is limited to DoD sites. How do we expand on that?
I think we as a collective group of professionals don't do necessarily a good job of aligning expectations when we're trying to test technologies. So we are often trying to get support from industrial clients or others to participate in these pilots and in-field demonstrations. And their expectation is that it's going to go and it's going to work. When our expectation is we want it to fail and fail fast so we can learn and improve it. So I think it's aligning expectations with the different user groups so they can first understand themselves as users. What definition of user do they fall into? Are they a early adopter? Are they a early majority, a late majority, or a laggard? So early adopters are those that really want the competitive edge. They're willing to accept risk. They're willing to accept trial and error and know that it is a process. Your early majority, they really want that solid evidence and case study that's already out there that someone did, and they could sort of step in as a next step to continue on once they have that solid evidence. And then late majority are those that really don't change much at all unless there's peer pressure or regulatory drivers to do so. And the laggards are traditionalists who aren't going to do anything unless their pants are on fire. So I think it's helping those users understand where they are and what risks they're willing to accept and having those conversations early on. We just misalign often, I think, an expectation when we go out and say we have this new great technology and get them all excited about them, but forget to really educate them on how that process works and where we are in the process.
Yeah, and that is a perfect segue to our next topic, Shailene, which is this, I would say, wave of contacts that we're probably all getting on a regular basis from companies and vendors wanting to promote and sell their latest groundbreaking PFAS treatment tech. And, in that same vein, there are press releases all the time on PFAS treatment breakthroughs, and clients see these, they contact us about them. And I think that plays into some of the misalignment of expectations that you're talking about. Shailene, when the buzz is this is a great new technology that's really going to work, and the reality is maybe something a little different. So the question is, how are we and regulators and the regulated community and the public supposed to process and evaluate some of these technology claims? And to put it bluntly, how do we separate the spin from the really serious solutions? I think that's one of the keys here.
Going back to the TRL levels, I think the first question is where is this technology in that readiness level process? Is it at concept stage and it's a promising concept? Then you can identify where and how you would interface with that. Is it in the demonstration stage or is it truly towards commercialization? And once you do that, understanding then yourselves, are you an early adopter, a laggard? Where do you fit in that user perspective? And does this align with me being participating in this? So I think that's a primary first step to really look at it. In terms of evaluating, is the tech valid? Do they have any publications? Do they have case studies to share? Do they have regulatory feedback that they can share? That also helps you define where it might fit and bin into the technical readiness level process. But as we discussed, that's not the only thing. That's not the only thing that will drive success or failure if you are a user. We also know the challenges with adoption and acceptance.
I would say building on that, I think a nuance is differentiating between the applicability of the technology. Because at some point, these technologies that are being marketed maybe worked in a certain scenario And so the vendors will market that. So the marketing does agree with the science. But I think the question as practitioners with a problem to solve is it going to scale to your specific circumstance? So even if it's a very well run pilot study, you test it under certain conditions with certain treatment targets and cost listings. But then is that going to translate to your scenario, which might be different in a number of ways? So it's trying to understand those ways and if it is it going to translate or is it going to be a totally different approach? So how do you scale those technologies to different situations?
Amita?
Yes, I can't agree with you more, Anna. I think that resonates so much with me as a practitioner. I think, in short, I would put it that one size doesn't fit all. It might be a technology that has been extremely successful in a lot of different sites, but will it really work at your site? Is it a suitable technology for your specific site in the specific condition that you need to apply? And that's not a question that we, let's say, daily face with PFAS. It's just PFAS, but it's with everything, every remediation or treatment project we do.
Yeah, it's not just about whether the technology works, right? A lot of these technologies do. They wouldn't be at the level they are if they didn't work at some level, but it's often about other things. What other technologies do we have to combine them with? What are the conditions at the site? Can it be scaled? What are the economics of it? So there are all these other factors that come into play. So that was great conversation. Thanks, guys. I want to close the discussion today with just some prognosticating from the three of you as seasoned practitioners here about where you see the current gaps in R&D for PFAS. If you had to put your finger on problems that really need solutions right now, what would those be? Who's doing the R&D in those areas? Is there promising stuff on the horizon? And do we expect to see solutions in those areas of weakness? Do we expect to see those solutions form over the near term? Maybe we're moving now beyond drinking water treatment. And what's the next priority in the process of triaging solutions to the PFAS problem? Where are those gaps and where are we going next?
So I can initiate this discussion. I have my wish list. They're just concepts, and I'll indicate which one I think is the most promising, at least in the short term. There's, a lot of people doing research in these areas, but certainly short chain PFAS treatment and remediation technologies. So short chain PFAS are 5 or 6 carbon, fluorinated carbons or less, just different definitions, but they're generally shorter than PFOA and PFOs, for example, but of the same carboxylate category. And they're very difficult to treat by almost all technologies that aren't bulk destructive technologies or separation and concentration technologies like reverse osmosis, for example. So I think that if we have regulation of short chain PFAS, and there is a starts of this in some states, it's going to be very challenging to remove those. Second, in situ destructive approaches, there's just nothing available. There's some R&D projects and pilot studies, but they're very narrow in their scope. PFAS-specific adsorptive media, and a secondary would be ability to regenerate without using flammable solvents or salt brines, which are difficult to treat the PFAS in those regenerants. And then finally, additional thermal treatment systems. There's a lot of research showing that hazardous waste incineration conditions do substantially destroy PFAS and a number of environmental media. But there's also research showing that products of incomplete destruction that are fluorinated are created, and that's an ongoing area. But regardless of that research, there's still very few incineration systems available. And so shipping that waste to those systems becomes cost prohibitive. That's just my list. I'm sure there's others in there.
That's a pretty extensive wish list, Anna, but I think a really spot on one. So, Shailene, want to give you an opportunity to offer your thoughts on that wish list. Are there additional things that you would put on there? And also, what's going on R&D wise in some of these key areas that Anna pointed out that maybe we want to keep track of?
Anna did a really great job of highlighting many of the needs, and there's likely more in the remediation area. I think some of the challenges we're seeing now is with the states shifting to product and process emissions, gathering better understanding and analytical capability to understand and measure those PFAS emissions, so to speak, whether it be in air, soil, water, or through a manufacturing process, is I think an area that is a next stage in addition to remediation and cleanup, is sort of trying to reduce that emissions discharge to the environment so that we can address those that have released as well as proactively look at what's continuing to be out there. Some industry specific organizations that are focusing on that, Semiconductor, SIA, Semi Industry Association, they're trying to look at where and how PFAS may be released across their process. So that's an example where industry is really digging in to do that.
Amita, what's your perspective?
I'm going to spin this question around a little bit because I got some time to think about it as Anna and Shailene were talking. So I think they covered most of the things that I would have in the typical bucket list, let's say. But what I would add is research doesn't end once the product is commercialized. And I'm trying to connect this to what we discussed previously. Even if there are several successful applications of a treatment technology, when it comes to applying that to your side, there is some level of research needed so that we bring it to a point where we can apply it at full scale. That's where I would leave you, that we don't want to call it research, but there is some level of research that is needed. And, my background is in research. So I appreciate it even more that it's not a commercial technology, that it's just off the shelf, you're taking it and applying it. There is a transition that needs to happen.
Great. Thank you, Amita. And just closing thoughts, Amita and Anna, is there hope moving forward that we'll continue to research and find solutions to these problems? I think the answer is yes, but just want to give you an opportunity to comment on that briefly.
I think the answer is yes, but it's going to be, I don't think we were expecting this 15 years ago. PFAS truly is a global crisis that has emerged in the last 10 years. It happened rapidly. But I go back to the concept that Shailene actually just mentioned, which is that it appears that dealing with PFAS is going in the right direction, in that PFAS are being taken out of products, out of commerce, and discharges, either wastewater or air emissions, are being examined. And that's very positive as compared to the chlorinated solvent. So in particular, perchloroethylene is a dry cleaning solvent, is still in commerce, even though we've been cleaning up chlorinated solvent sites for 25, 30 years, and has just recently been, I think it's going to be phased out in the next 10 years. So with PFAS, there's hope, I think, in that these contamination problems are going to be prevented in the first place from happening because PFAS are being taken out of commerce except for the essential uses.
I would agree. And I would say I'm also optimistic about this situation. I think it's not just the science and research of treatment, but overall, as human beings, we have come a long way in understanding this issue. And our perspective towards handling this and other issues that we face in the environment is definitely changing, and it's improving for the better. So I do see light at the end of the tunnel. Maybe the tunnel is a little longer than we have seen before, but I think there is a good story to tell about it.
Yeah, and of course, adding to the hope here is the fact that the three of you are great seasoned professionals that are practitioners in the field and are going to continue to work on technology, innovation, and implementations at some of the most challenging sites. And so with that, everyone, I just want to thank you so much again, Shailene, Amita, Anna, for joining me today on Challenge Accepted. It's been an incredible conversation. Thanks a lot, everybody, and have a good day.
Thanks, Adam.
Thank you.
Thanks for listening to Challenge Accepted, PFAS. If you like what you heard, please like, subscribe, and write a review on Apple, Spotify, or wherever you get your podcasts. For more information, check us out on LinkedIn and Instagram at Langen, ENGENV, or visit langen.com/PFAS. See you next time.
This podcast was edited by Resonate Recordings.